Hi, and welcome to the research presentation on anomaly detection in the joint angle sensors of a snake robot. My name is Luke Fina, and I will be presenting today. The main things we'll be going over are the dynamic system modeling, the joint control, the developed anomaly detection algorithm, and then the simulation results. To begin with, most snake robots over the past 45 years have been considered a kinematic chain with non-holonomic constraints to avoid a lateral slip. These constraints aren't really realistic due to real biological snakes accomplishing this through friction properties. So a new dynamic model needed to be created to actually account for this, and that's what we did. Also, this control algorithm is implemented on a planar 4-link snake robot. Advantages of snake robots are that they're highly stable, highly adaptable, they have a good cross-section size, and they're highly redundant. The disadvantages are that they can only carry a very low payload, they have a low speed, they have a high degree of freedom for control, which leads to more complicated control laws being needed, and then they have a high energy consumption. Main applications are not limited to these, but some of them are exploration, inspection, the medical field, and hazardous environments. Here are some examples of different snake robots that have been done in the past and are currently being worked on. The ACM, Caltech, CMU, and MIT snake robots. The dynamic model begins with the standard nonlinear format. Keynes' method is used to derive the equations of motions as you see on the left. On the top right, you see the 4-link snake robot planar view. There are 6 degrees of freedom and 6 generalized coordinates due to no side slip constraint. Also, in the bottom right, you can see the free body diagram of the snake robot link, where the black dots are the reactionary forces, and then anything about the white dot in the middle is about the center of mass, and I is per link. To create the motion for serpentine gain, sinusoidal motion is necessary, as you can see in phi. And the mode of control that was used is the sliding mode control. And then with the sliding mode control, the Lyapunov function of 1/2 S transpose S is used. And then also just the standard block diagram for most feedback control systems, where the controller feeds into the dynamic model, and then there's a feedback element with the error and the different states. A parity space approach with chi-square test hypothesis used. The aim is to create residuals that represent the difference between expected joint angles and actual joint angles. This main assumption is that all the angles are the same, they just have a difference in phase shift, so it makes them much easier to be compared. Here's the mathematical representation of what that is. You have the measured joint angles phi 1 through 3 on the left, and the measured joint angles equal the combination of the joint angle states, the Gaussian noise, and the fault values. Also to note, K1 and K2 are the phase shift values between the joint angles. In matrix form, this is the following way of K equals A of yk plus epsilon k plus f to the k. In order to eliminate the measured state variable, we can multiply vector A on the left by row vector v such that the following. The left null space of the matrix A consists of all vectors v such that they satisfy v of A equals 0. In our particular case, the left null space of A has a 2 dimensions, hence it's V1 and V2 as you can see in the bottom right, and they span the entire left null space. If both sides are multiplied by the matrix V, the equation becomes the following. And then let's define it as tau of k. This variable is what we end up calling and defining as the residual, and it indicates the inconsistency exhibited in the system of Vi. For the no anomaly case, where f is 0, the residual becomes smaller and much less complicated, where the f term cancels out. If one transforms the residuals, the normalized residuals are equal to the following. As a result, the residuals in no anomaly case would be as residual samples lie within a disk around origin. The size of the disk is defined by the noise variance. In the anomaly case, we can't assume that f is 0, so it adds an element to the matrix where it equals the following, since f is non-zero. For detection, in order to detect, we use a statistical approach where either h naught is such that e of tau equals 0, or h of 1 where it does not equal 0. Acceptance of the hypothesis depends on the second degree chi-square test, such that the following is true, where chi squared of 2 is tau 1 squared plus tau 2 squared equals gamma. The chi-square test is based on the lookup table giving the threshold h corresponding to the false alarm probability alpha, which is seen there. In order to detect the anomaly, the chi-squared random variable gamma is compared to h. If gamma is equal or smaller than that value, this results in an acceptance of h naught. Contrary, it'll be acceptance of h of 1. It should also be noted that these evaluations include a false alarm probability that is alpha. To isolate, the assumption in this study is there is only one anomaly in the system at a given time. By checking the relative angle difference between residual vector and column vectors of vector v, the origin of the anomaly can be indicated here. For simulation results, the simulation experiment was accomplished by using 3 joint angles. There is a phase shift between the different joints, and time delays are introduced for all the sensors, where there's a 0.17 second time delay between sensor 1 and 2, 0.33 second time delay between sensor 1 and 3. The 2 cases are the following, where there is no anomaly and then there is an anomaly where the fault is injected. In each joint angle sensor mode, there's a measurement noise added. It's assumed that all the sensors are fault-free and identical. It's also assumed that only one sensor at a time has an anomaly, and the simulation is run for 30 seconds. The anomaly detection subsystem is passive in this simulation, so it has no bearing on the feedback control system. In future work, the anomaly detection part will be incorporated into the control system, but in this case it is not. As you can see, these are the simulation results from no anomaly. On the left half you can see phi1 through phi3 where there's a Gaussian noise. And then you can see on the right where there's an alarm index and a sensor index. The alarm index indicates if there is or is not an anomaly. 0 is that there is not an anomaly. 1 is that there is an anomaly. The sensor index indicates which sensor the algorithm determines is at fault. In this case, there is no sensor at fault because there's no anomaly. It should also be noted that, as described in the math earlier, there's a probability of alpha where there are false positives, and in this case it's 1%. Here's the case where there's a fault injected. It's injected between 15 seconds to 25 seconds, as you can see in feed 3. You can also see within the algorithm, within the alarm and sensor index, that it is correctly identified as an error in the alarm index, and that in the sensor index, the sensor 3 is determined to be the one at fault. So both are successful. In conclusion, the anomaly detection method for a joint angle sensor of a snake robot is introduced. The chi-squared hypothesis is adopted, and isolation is performed by comparing orthogonal projections of 3 joint angle sensors. Simulation results are presented with successful implementation of the anomaly detection. Future work, aside from implementing this anomaly detection into the control feedback system, is going to be focused on different types of faults like gain type, and also just creating an overall robust fault tolerant controller for a snake robot. I would like to thank the University of West Florida, especially the Department of Intelligent Systems and Robotics, and the Civil Research Group for making this possible. I would like to also thank the New Mexico State University and their Department of Mechanical and Aerospace Engineering, and the Biorobotics Laboratory for making this all possible. Thank you so much.